Hi there, welcome to this video where we continue taking a look at Leonhard Euler's Introduction to the Analysis of Infinities. So in this video we continue taking a look at chapter 9 of the first volume. In the last two videos that I've uploaded where I started looking at this, I've made it up to section 154. In this video, therefore, I'm going to be starting from section 155 and going through to... I'm not going to be going through all of this chapter. I think I'm almost certainly going to go up to and including section 158, possibly 159, although possibly not. I think we'll see how I feel. But I think once I've got up to and including section 158, really what Euler does from that point forward is fairly clear. Okay, I've really covered the main points of this chapter. With the exception of a few miscellaneous comments that I want to make on some of the notation that he uses in some of the sections, such as section 161 or 162, for example. There's nothing that I really want to say beyond section 159. Okay, so hopefully I should say everything that I want to and need to say in this video, covering section 9, chapter 9, sorry. As we go through this video, there's going to be a few instances where I'm going to have to just kind of break away from what Euler's doing and just try to explain a little bit some of the techniques that he's using, because some of the techniques that he uses are initially quite strange from a modern perspective. They would probably be considered quite unacceptable from a modern perspective. There is a logic to them. That it's not necessarily unreasonable for him to be using these techniques, but I need to try to explain at least my own interpretation of what I think Euler is doing and how he's using these kind of weird techniques. Okay, so let's make a start then. So we're on with section 155. So I've still got all my stuff from the last video in here. Maybe I should have cleared that off beforehand, but never mind. So just while I'm doing this, I'd be really grateful if you would subscribe to the channel, hit the like button, and leave a nice positive comment in the comments section. It's always very much appreciated. Okay, so here we go then, section 155. So what he's saying here is we've seen above that e to the power of x is equal to, I can't see it properly on the screen, 1 plus x over 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3 plus, and so on, okay, plus etc. So this was shown in a previous section, a previous chapter. Which one was it? Probably chapter 7, I think. I think it was chapter 7 where he gave the series expansions of e to the power of x and the natural logarithm of x. Section 8, I think he goes through the trigonometry. I could be wrong on that one, but anyway, it's in a previous chapter. He's also shown in the same chapter that e to the power of x is equal to 1 plus x over I to the power of I. Okay, where I denotes an infinite number. Okay, so here's the first point at which I'm going to have to just break away for a little bit. In fact, I'll stay on the same page. So Euler uses this symbol I commonly to represent an infinitely large number. Okay, so don't be mistaken here. I does not stand for what we conventionally use I for in modern mathematics, which is one of the square roots of -1. I here is representing an infinite number. So Euler seems to treat when he uses I to represent an infinite number, he seems to see this, to view it as some kind of integer. Okay, an infinitely large integer. A lot of the properties that he ascribes to this symbol are similar to the kinds of properties that integers have. Now, because this is an infinitely large number, he does distinguish it somehow from the finite integers. It does have particular properties that are peculiar to it, which we'll encounter as we go through this section and the subsequent sections. But he does seem to treat this as some kind of infinite integer. Okay. Obviously, this wouldn't be acceptable from a modern perspective, but he didn't have the kind of limit concepts that we have now. Okay, the limit concept in the precise form that we use it now wasn't available to him at that time. Okay, so he does have in mind here something along the lines of what we think about when we think about a limit. So when we write, for example, now that e to the power of x is equal to the limit as n approaches infinity of 1 plus x over n to the power of n, for instance. Okay, maybe he did have something like this in mind. Okay, but I'm not going to use. We're not using the limit form. The whole point of what I'm doing here, going through Euler's work in this video and my other videos, is to present Euler in his own words, so to speak. Okay, so I present the techniques that he uses in the way that he uses them, and even if from a modern perspective these techniques are a bit suspect, a bit of a no-no from time to time, they're still the techniques that we use. Okay, and it's not necessarily unreasonable for him to use these techniques. He does arrive at some correct conclusions. Okay, obviously the reasoning, again, from a modern perspective, is flawed, but he does arrive at some fairly robust conclusions. Okay, so let's get rid of that. So we will be using these infinitely large numbers. Bear in mind as well that for these infinitely large numbers, let's say we've got, for example, k, which is a finite number, not necessarily an integer, k over I, something like that. This would represent an infinitely small number. Okay, he does actually use these earlier in the book. Where does he use them? Maybe about chapter 6-ish. Maybe, yeah. No, sorry, it's chapter 7. Yeah, it's when he's finding the series expansions of exponential functions. He uses infinitely small numbers, infinitely large and infinitely small numbers, kind of side by side. So you can have an infinitely large number multiplied by an infinitely small number, giving a finite number. How does this work? Well, there does seem to be a particular logic behind how he uses these. And that logic can seem a little bit suspect from a modern perspective, but that's how he works, okay? And these infinitely small numbers, they're sometimes they can be considered as having a negligible contribution. Sometimes they're considered as having a non-negligible contribution. Okay, we'll see this as we get further into this section, that particularly when we've got an infinite number of factors all multiplied out, and we multiply all of these factors out, and each factor has an infinitely small part to it. It doesn't necessarily, we can't just necessarily eliminate it, because it might be that, in Euler's opinion at least, that when we expand out these infinite factors, the infinitely small contribution from each factor actually results in a finite and non-zero contribution to everything, the whole thing, when it's been expanded out. It seems a bit fishy from a modern perspective, but this is how we're going to be working. Okay, so on with the show. So what he says here is, it is clear that the series 1 plus x squared over blah, 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 has an infinite number of simple factors which are equal. Interse iguales, nempe 1 plus x over, namely 1 plus x over I. Okay, so there's an infinite number of factors of this. Sorry, not of this. Well, yeah, actually, okay, because this expansion here and this expression here, they're equal, then we can see that from this there are an infinite number of factors of the form 1 plus x over I, infinite number of simple factors, which must be, therefore, factors of 1 plus x over 1 plus x squared over 1 plus 2, and so on and so forth. Okay. So, if from this series the first term is subtracted, then we will have x over 1 plus x squared over 1 plus 2 plus x cubed over 1 plus 2, 1 times 2 times 3, plus and so on, going on to the next page, is equal to e to the power of x minus 1, which in turn is equal to 1 plus x over I to the power of I minus 1. So in other words, we get x over 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3 plus and so on is equal to e to the power of x minus 1, which in turn is equal to 1 plus x over I to the power of I minus 1. Okay, so this is going to be worth bearing in mind. It's also worth noticing that this can be written as x times 1 plus x over 1 times 2 plus x squared over 1 times 2 times 3 plus and so on. Okay. So what he does then, he says cuyos forme so the form of which can be compared with that of section 151 with a equal to 1 plus x over I, n equal to I, and z equal to 1. So if you remember in section 151, which I went through in the previous video, right at the beginning of the previous video, we were interested in developing a technique, or Euler was interested in developing a technique for finding the simple or linear and quadratic, real simple and quadratic factors of expressions of the form a to the power of n minus z to the power of n. Okay, and it turns out that the factors are of the form AA, or the potential factors, potential quadratic factors are of the form AA minus 2az cosine 2k pi over n plus zz. Okay, where k is, so 2k is a non-negative integer, so 0, 2, 4, 6 is less than or equal to n. Okay. What else is there to say about that? Right. So, oh yeah, and there is a little adjustment that we need to make in the case where we've got 2k equal to 0. Remember, this quadratic factor, all the technique does that Euler shows us is throw up these potential quadratic factors. Sometimes, though, the potential quadratic factor is not an actual quadratic factor, yet we can still extract a simple or linear factor from it. So in the case when 2k is equal to 0, we get, for example, that we get this will reduce, because cosine of 0 is equal to 1. We get a minus z squared as a potential quadratic factor, but it turns out to not be an actual quadratic factor. However, a minus z is a linear factor, okay, of a to the power of n minus z to the power of n. So I go through this in more detail in the last video. There is also the case when 2k happens to be equal to n, which we're not going to have to worry about in this video, because we're going to effectively be taking n as an infinitely large number, and therefore if k is finite, then 2k is never going to be equal to I. So we'll have to bear these kinds of things in mind. Let me get rid of all of that. And the form of this is going to be really important to us, because what Euler is going to be doing is going to be finding the factors of this, the linear, but more interestingly, the quadratic factors of this, and he's going to have to rescale the factors. And it's this number here, the 1 here, that is going to tell us how to rescale those factors. Okay, this x here also tells us how we're going to have to rescale one of the factors. Okay, so we compare this with that form then from section 151 with, as we see, a equal to 1 plus x over I, n equal to I, and z equal to 1. So what we can see here is that what Euler showed in that section, in section 151, we only really worked with finite values of n. Okay, so he gave us a technique that shows us how to find the real factors, whether linear or quadratic, of that expression a to the power of n minus z to the power of n, where n was typically assumed to be finite. But now he's just starting to apply that technique to when n is infinite, an infinitely large, let's say an infinitely large integer. Now, obviously, from a modern perspective, this is very suspect. You wouldn't do this. It wouldn't be considered legitimate to make that jump from finite to infinite. Just because something works in the finite case doesn't mean that it automatically works in the infinite case. Nevertheless, that's what he does, and that's what we're going to be doing here. Okay, so therefore, the factors, the potential quadratic factors of 1 plus x over I to the power of I minus 1 are going to be of the form 1 plus x over I squared minus 2a, which is 1 plus x over I z, cosine of 2k pi over n is I, plus z squared, or z times z, which is just going to be 1. Interestingly, I don't know why this is, but sometimes Euler uses, for example, x squared. In other cases, he uses xx. And similarly for z, he'll use z squared quite happily, and then other times he'll use zz. There doesn't seem to be any particular pattern to his usage. Sometimes it's one, sometimes it's the other. So when I'm working with Euler, I'll have a tendency to use both notations. They both seem acceptable. And when I'm working through, such as this, or in my other videos where I go through, say, Principia Mathematica, I tend to use the notational norms that are established in those works. I don't necessarily try to... So if Euler's quite happy using x squared or xx, I will use whichever I feel as well. And unless I can at some point determine a pattern to his usage, which I haven't as yet managed to do so, but if anybody else does know, has figured out, then I'll be all ears. But for the time being, I'll use whichever notation I see fit. Okay. Right, so in the case where 2k is equal to 0, we still need to make this little adjustment. So in this case, we will get as a potential quadratic factor 1 plus x over I squared minus, so cos of that is going to be twice 1 plus x over I plus 1, which is of the form a squared minus z squared, which is going to reduce to 1 plus x over I minus 1 squared. So it's, which of course reduces to xx over I, and that's what Euler is pointing out here. When we set 2k equal to 0, this produces the quadratic factor xx over I. But because of our little adjustment that we need to make, because we can see that xx over I is not a quadratic factor of 1 plus x over I to the power of I minus 1, because we know that this is also equal to x times whatever's in this bracket here, we can see that it's actually x over I, which is a factor, rather than xx over I. Okay, so it's exactly the same adjustment that's made there in section 151, but we need to make a further adjustment, okay, because notice the factor here that we see is x. So this factor that we've got from this technique, x over I, it needs rescaling. So we're going to multiply it by I. Okay, is this legitimate? Well, okay, just let me go to a blank page, and I'll kind of maybe explain how I see this working. So let's say we've got something like 2x squared minus 8. Yeah, minus 8. Okay, so this will factorize. So I'm fully aware that you can take 2 out as a common factor here. I'm actually going to leave it there because this is the point that I want to make. So this factorizes. It can factorize to, for example, and it's not the only possibility, 2x minus 4, x plus 2. Okay, so 2x squared plus 4x minus 4x minus 8. Okay. So we get 2 factors here, 2x minus 4 and x plus 2. But we can take 2 out of this factor. We can take 2 out as a common factor, and we get x minus 4. Sorry, not x minus 4, x minus 2. So x minus 2 is also a factor. So, but x minus 2 is just, it's half of 2x minus 4. Okay, so in other words, we can kind of adjust what exactly we consider as a factor. It is really up to a constant multiple. Okay, so we can have x plus 2 as a factor, but also we could consider 2x plus 4 as a factor. Okay, we could take the 2 out of the other bracket, out of the 2x minus 4, and shift it over into the other bracket to give 2x plus 4 as a factor. Okay, so our factors are really, they're factors up to a constant multiple. X plus 2 is a factor, 2x plus 4 is a factor. We could even say 4x plus 8 is a factor, or 3x plus 6 is a factor. It might make things a little bit awkward elsewhere, but we can do this. We can rescale factors, right? We can multiply them by constants. Well, here we're dealing with finite numbers, but we can do the same really with infinite numbers as far as we're concerned. So this factor that we've got of x over I, we're going to rescale, and we're going to have, instead of x over I, we're going to have x instead. So therefore, what he says here is that setting 2k equal to 0 produces the quadratic factor xx over I, which we ought to take x over I as we should only take x over I as a factor. Therefore, ergo x factor expressionis e to the power of x minus 1. Therefore, x will be a factor of the expression e to the power of x minus 1. Okay, so we can see that we need to do this, or it makes sense for us to do this based on what we see here. So it's a natural question to ask, how should I know to do this, to make these adjustments? My answer to that is based on what you see, okay, and your understanding of the context. So I mentioned this in a previous video. much depends on the context and your understanding of the context. Whether and how a technique applies and exactly how it's to be applied really depends on your understanding of the context. Euler doesn't necessarily spoon feed everything to you like it would be in a modern context where everything would be precisely stated and worded in a theorem, the precise conditions under which a technique can be used, and if the technique is to be applied, how it's to be applied, so on and so forth. It's all set out for you so that you just follow the steps in many, not always, not literally just follow the steps. You still need to have an understanding of the context, but it's much more objective, is what I'm trying to say. Here it's much more subjective. There's much more that depends on your reading of the situation, your understanding of the situation. So if you see that it makes sense, as Euler sees here, that rather than saying x over I is a factor of 1 plus x over I to the power of I minus 1, rather than saying that x over I is a factor, we say x is a factor, then we do that. Okay, and we're going to see in a second, we're going to be going even further with this idea. Okay, so let's move on then. I'm kind of running out of space, so I'll tell you what I'm going to do. I'm going to copy that because I want to leave those notes up. Okay, let me get rid of this stuff. So again, just while I'm doing this, if you haven't done so already, please feel free to subscribe to the channel. Also, if there's any ideas that you have about things that you'd like to me to go through on this channel, any works that you're interested in that you want to know more about, or you want to get my take on, please let me know. And if I've got time to do it, then I will do. And if it seems like it's something that I'd be interested in going through. Okay, so for the remaining factors, right, okay, so from the cosine, so 2k pi over I is infinitely small. So he's saying the arc 2k pi over, because we're using this in the context of cosine. Cosine 2k pi over I. So we understand 2k pi over I as representing an arc of a circle. But it's an infinitely small arc. Now, what is established in, I think it was chapter 8, is the series expansions of cos x and sin x, for example. And we get the familiar kind of approximations to cosine for small angles, the small angle approximation to cosine, except he uses it as an equality. Okay, so he says, for example, that cosine 2k pi over I is equal to 1 minus, and it will be 2k pi over I squared over 2. Right, so we get 2k pi I squared over 2, which is going to be equal to 1 minus 4kk over I times pi over 2, which of course is equal to 1 minus 2kk over I times pi, and that's what we're getting here. So cosine 2k pi over I is equal to this. So we're using it as equality. Again, this would be a bit dodgy from a modern perspective. We would think of it as an approximation. But we're dealing with these infinitely small numbers. Okay, so they work a little bit differently. So we can have equality here. And he says the following terms, since I is an infinite number, in nihilum abeuntibus, so they decrease to 0. Okay, so therefore the factors, an arbitrary factor of our expression So that 1 plus x over I to the power of I minus 1 has arbitrary factor 1 plus x over I squared minus 2 1 plus x over I. So remember, it's cosine 2k pi over I, but we've already shown, or Euler's already pointed out, that this is equal to 1 minus 2kk over I pi pi. And plus 1. Okay, so I'm dealing with this here, plus 1, which after simplification yields this expression here. I'm not going to go through it all on the screen here, but we get xx over I. It just expands, simplify effectively. Xx over I plus 4kk over I pi pi plus 4kk pi pi over, I can't read it properly, I cubed. Yeah, okay, over I cubed. Right, so, okay. So he says something then, he makes it a bit of a jump here. So he says, therefore, e to the power of x minus 1 is divisible by 1 plus, so let me write it here, 1 plus x over I plus xx over 4kk pi pi. So we've derived this expression for one of the for an arbitrary quadratic factor. So here we're assuming that k is greater than 0, is an integer that's greater than 0. So it's going to be a genuine, honest quadratic factor. We derived this expression, but now he's jumped to this one and said, actually, no, this is not the factor that we want. It's actually this. He doesn't explain where this comes from terribly clearly, but it's because, again, he's rescaled the factor. He's rescaled it so that the constant term, and the constant term here is this. Well, okay, no, he's rescaled it so that there's a 1 here. Okay, so it's not actually the constant term as such, but where is it? What is he divided through by? 4kk. Right, so it's actually this that becomes the 1 here. Okay. So that term matches up there, that term matches up here, and then this term, no, it doesn't. Where did the x go? I've missed out an x somewhere, haven't I? Oh, right, yeah. There it is. Missed it off there. Missed off the x there. So, okay, so let me get this right then. So the xx over I corresponds to this term. So yes, this is actually a constant term then. This 4kk over I pi pi is the constant term. Okay, so that's how the terms match up. So what he's done is, to get from the first one to the second one, he's divided through by 4. I'm just looking at my notes here. So it's 4kk pi pi over, well, in fact, it's just this term here. He's divided through. Now, why has he done that? Well, remember what I said earlier, that it's important to pay attention to the form of what we see in here. and in particular that we've got this 1 here. So I'll just take a little, do a little aside again. So if we've got, for example, 1 minus x minus 2x squared, for example, this can be factorized, I hope. Thinking off the top of my head here, but 1 minus 2x plus x, okay? Forgive me if this is wrong, but it should factorize to 1 plus x times 1 minus 2x. Notice that we've got a 1 here. And what do we see? In our factors, 1, 1. Okay? Now, of course, we've seen that we can rescale factors and things like that. So we could have, for example, a half plus a half x times 2 minus 4x would also be a possible factorization. But for simplicity, it makes sense for us to have these numbers here as 1 rather than a half and 2. There's nothing stopping us from having this factorization, this awkward factorization, but it makes sense for us to have our factorization like this. So what we're aiming for here, go back to what we're talking about here, we're trying to find a factorization of this 1 plus x over 1 times 2 plus x squared over 1 times 2 times 3 plus and so on. The initial number, the constant here, is 1. So it makes sense for us to have all of our factors having a 1 as their constant term. So that's what he's doing here. Rather than having this weird constant term 4kk over ii times pi pi, he rescales the factor so that we've got a 1, okay, as the kind of leading term of the factor, the constant term of the factor. Okay, so he rescales every single one. That's the justification for it. Again, how are you supposed to know to do things like this? It's based on your observations, or in this case, Euler's observations, and understanding of the context and what you're trying to do. Actually understanding what you're trying to do. So, what Euler does then, I'm going to need another page, because I don't really want to erase all of that permanently. So what he does then is he takes these factors, there's one for each value of k, and he gives a factorization for our expression. So in particular, we've got this 1 plus x over 1 times 2 plus x squared over 1 times 2 times 3 plus da 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 da. He says that this factorizes to 1 plus x over I plus xx over 4 pi pi times 1 plus x over I plus xx over 16 pi pi, and so on and so forth. There's going to be an infinite number of terms, but importantly, even though there's an infinite number of terms, we can still assign a number to the number of terms, number of factors, which is I over 2. Okay, so we don't assume here that I is equal to I over 2 and things like that, even though arguably it might be if it's an infinitely large number. But these infinitely large numbers, again, there does seem to be a logic with them. It's not a logic that I've managed to pin down with any definiteness at this stage. But nevertheless, I over 2, that's what we're going to be. We're going to use the expression I over 2. The idea is now that when all of these factors are going to be expanded out, so he's not happy with this, right? He's not happy with this. As we see in the, if we move on to section 156, he says, quatem hi factores continuant partem infinite parvam x over I. So he's saying, since these factors each contain an infinitely small part, x over I, which appears in each individual factor, then by when all of them are multiplied out, atque per multiplicationem omnium, quorum numerus est half I. So when they're all multiplied out, all of these factors, the number of which is a half I, then what we'll find is that from each term, from each factor, we will get a contribution of x over I. So we'll have x over I plus x over I plus x over I. How many of these will we have? I over 2, or half I. So the contribution of all these x over i's to the overall is going to be x over I times I over 2. Cancel, cancel, which is, x over 2, which is finite. Okay, so even though we've got this infinitely small contribution from each of these factors, their total contribution when everything is expanded out is not infinitely small. So what he's not happy about is, and what he says here is, he doesn't like that this infinitely small term can't be eliminated from each of these factors, because of this fact that when expanded out, it yields a finite non-zero contribution to the whole. He says, in order to avoid this, let's consider instead the expression e to the power of x minus e to the power of minus x equals all of this business here. Okay, so he changes tracks now. He says, right, we've done that. I'm not happy with it. This is how it works. This is the result, but I'm not happy with it. So let's do something else now. Okay, so let me get rid of all of this. So now we consider e to the power of x, what was it, minus e to the power of minus x, which is equal to, on the one hand, 1 plus x over I to the power of I, again, I is an infinitely large number, minus 1 minus x over I to the power of I, which in turn is equal to twice x over 1 plus x squared over 1 times 2 times 3 plus, and so on. Okay, so what he's going to do now is he's going to do a very similar thing to what he's just done. But what we'll end up with in this case is a series of factors, an infinite number of factors, none of which has this infinitely small part to it. Okay, which is much more, it's much more desirable in his opinion. Okay, so how are we going to do this? So we compare this form again with the form of section 151, a to the power of n minus z to the power of n. But in this case, we let a equal 1 plus x over I, z equal 1 minus x over I, and n is equal to I. Okay, so let's move on. So we're on to section 156 now. He just emphasizes here that e to the minus x is equal to 1 minus x over 1 plus x squared over 1 times 2 minus x cubed over 1 times 2 times 3 and so on. Okay, so who use right? So again we've got the it's this expression here that we're trying to factorize effectively. I'll find the factors of. And the factors are going to be of the form AA minus 2AZ cosine 2k pi over over I plus z. So he uses the same trick that because 2k pi over I is infinitely small, we can say that cos 2k pi over I is equal to 1 minus, well, we've already gone through the calculation, so it's 2kk over II pi. So substituting in our values of A and Z and this approximation, then we get 1 plus x over I squared minus 2, 1 plus x over I, 1 minus x over I, 1 minus 2kk over II pi plus 1 minus x over I squared. Okay. Which, again, expand, simplify, and what we end up with is 1 plus, and also rescaling the factor if necessary, kk pi minus xx over II. So ubi autem terminus tuto omittitur quia est. So what he says is that this term here now, so this is an arbitrary factor, right? This is an arbitrary factor for us. So for the various values of k, it doesn't really say what. So as before, if k equals 0, the first factor is equal to x. Oh yeah. Because of course you can take x out of this as a common factor, right? So yeah, we've, as before, exactly as previously, if k equals 0, this will reduce to a minus z squared, which that's not a factor, it's a minus z. But a minus z is going to be equal to, what did we take a and z to be? A minus z, right, so it's going to be like 2x over I squared. So a minus z is going to be 2x over I, but we rescale that and just make x the factor, okay, if need be. We certainly get rid of the I anyway. But the genuine quadratic factors are going to be of this form here, where k is just a positive integer, okay? So, but if we've got an infinite number of factors of this form, when we expand out, what are we going to see? We're going to see from each factor a contribution of minus xx over II. But how many of those terms are we going to see? I over 2. So we're going to get I over 2 times, let's forget about the minus sign, xx over II, which of course is just equal to xx over 2I. So this is an infinitely small number. So this infinitely small contribution to this factor is going to lead to an infinitely small total contribution when everything's expanded out. Okay, so therefore, in this instance, it can be omitted. And that's what he does. He omits that part of the factor. So what we're left with is just 1 plus xx over kk pi. Okay, as our factors. That's what he's getting at Right, so the term xx over ii can be completely omitted, since when it's multiplied by I, it gives an infinitely small. It's infinitely small still. It stays infinitely small. We've dealt with the case when k is equal to 0. So the factors. So, okay, let me go on to another page. And just clear a bit of space. So if you remember, we were dealing with e to the power of x minus e to the power of x, which was 1 plus x over I to the power of I minus 1 minus x over I to the power of I, which in turn was equal to twice, well, we can write it as 2x, 1 plus x over 1 times 2, plus x squared over 1 times 2 times 3, plus etc. So what he does now is he divides through by 2. So that will become a half. Gets rid of the 2 from there. And what he says is that this factorizes then to x times 1 plus xx over pi. That's when k is equal to 1. 1 plus xx over 4 pi, so that's when k is equal to 2. 1 plus xx over 9 pi, that's when x is equal to 3, and so on. So that gives us our infinite factorization of e to the power of x minus e to the power of x over 2. And notice that there's no infinite part to any of these factors here. Okay, so we've made it. We've made it to the end of section 156. Let's keep going. Okay, so we're on to section 157 now. So let me go into a new page. And get rid of this. So he's going to do a similar thing now for e to the power of x plus e to the power of minus x over 2. Okay, using the result from section 150. So in the same way, e to the power of x plus e to the power of minus x over 2 is equal to, so it's, in this case, it's 1 plus xx. So we don't get the common factor of x here. 1 times 2 plus x cubed over 1 times 2 times 1 times 2 times 3 times 4 plus etc. Oh, sorry, that should be x to the power of 4. Forgive me. And this is also equal to a half 1 plus x over I to the power of I plus 1 plus x over, 1 minus x over I to the power of I. So we're comparing with the result from section 150. So it was a to the power of n plus z to the power of n, with a equal to 1 plus x over I, z equals 1 minus x over I, and n equal to I. Remember, the quadratic factors of this we found to be of the form a, or the potential quadratic factors a plus, no, let me get it right actually. Was it plus or minus? Minus. Still minus. Minus 2az cosine, and it was 2k plus 1 pi over, in this case, over n plus z. Okay, so that's what he's saying here. we use expression. A factor of this expression will be AA minus 2AZ cosine. Oh, no, sorry. Wrong page. On to the next page. Where are we? Right, here we go. Right, a factor of this will be, an arbitrary factor will be AA minus 2AZ cosine 2k plus 1 pi over n plus ZZ. So plugging all of the values in, we get this, and doing a bit of simplification, 2 plus 2xxii over ii minus twice 1 minus xx over ii cosine 2k plus 1 pi over I. Therefore, again, using this approximation, cosine 2k plus 1 pi over n is equal to 2k plus 1 minus 2k plus 1, so x squared over 2, yeah, pi over 2ii, and again with equality, plugging that into here, then, and expanding, simplifying, I'm not going to do it all here, we get the factor comes out to be 4xx over ii plus 2k plus 1 squared pi squared over ii. The term which has I to the power of 4 in the denominator, so when you expand out and simplify and everything, you'll get terms with I to the power of 4 in the denominator. These vanish. Quoniam ergo omnis factor expressiones. Okay, so all factors of the expression 1 plus x squared over 1 times 2 plus x to the power of 4 over 1 times 2 times 3 times 4, etc. are of the form 1 plus... I can't read that properly on the screen. Alpha xx. Okay, so again, he's rescaling the factors here. Where... so he's saying here to bring the factor into this form, to reduce it to this form, it's necessary to divide by 2k plus 1 squared pi squared over ii, and therefore the factor, an arbitrary factor, will be 1 plus 4xx. So alpha is equal to effectively 4xx as 4 over 2k plus 1 squared pi, from which all factors, all infinite number of factors can be found, and if in place of 2k plus 1, all successively all odd numbers are substituted, and therefore we get the factorization e to the power of x plus e to the power of minus x over 2, which equals 1 plus x squared over 1 times 2 plus x to the power of 4 over 1 times 2 times 3 times 4, and so on. The factorization is as given here. So it's 1 plus 4xx over pi times 1 plus 4xx over 9 pi, and so on and so forth. Okay, so it's very similar to the previous case. There's no point in me going into excessive detail on it. So then in section 158, I'm probably not going to go through section 159. So I think the video's gone on long enough already. But I will just take a quick look at section 158. So in section 158, what he does is he... well, just let me get rid of this and I'll explain. So if x is an imaginary quantity, so if we let x equal z square root of minus 1, then e to the z square root of minus 1 minus e to the minus z square root of minus 1 over 2 square root of minus 1, which is equal to sine z. This is equal to, by section 100 and using the result from section 150, which section are we up to? 156, with x replaced with z, it's going to be equal to z minus z squared, z cubed over 1 times 2 times 3 plus z to the power of 5 over 1 times 2 times 3 times 4 times 5 minus and so on, etc. Which saber factores numero infinitos. So it's z. So, okay, remember this had a factorization so each of the factors was originally, let me find it, 1 plus xx over kk pi pi. So now if we replace x with z to the power z multiplied by square root of minus 1, then this will become 1 minus zz over kk pi pi, which in turn is equal to 1 minus z over k pi, 1 plus z over k pi. So that leads to the factorization of sine that you see here. Okay. Sorry, not on that line. On here. Sine z is equal to z times 1 minus z over pi. So k is equal to 1, 2, 3, 4. So z over pi and 1 plus z over pi, they correspond to when k equals 1. 1 minus z over 2 pi. 1 plus z over 2 pi, that corresponds to when k is equal to 2. Both of them correspond to when k equals 2. 1 minus z over 3 pi, 1 plus z over 3 pi, both correspond to when k equals 3. And you can do a similar thing. So I can't read it properly on the screen there. Okay, so yeah, so you can see that sine z will be equal to 0 when z equals 0. Using this factorization, when z equals 0, when z equals pi, when z equals minus pi, when z equals 2 pi, when z equals minus 2 pi, when z equals 3 pi, and when z equals minus 3. It's exactly what we expect from the behavior of sine, right? Sine, it's this periodic function. It goes through the origin, up, down through pi, down, up through 2 pi. So effectively the factorization that we see here, it's it's almost like an infinite version of the factor theorem. Okay, you're looking for the zeros of the function, but it's sine z, it's well, okay, we're treating it like a kind of polynomial here, but obviously an infinite polynomial, what we call a power series now. But we're kind of applying the factor theorem to this infinite polynomial, in a sense. Again, from a modern perspective, not really valid, not quite right, but that's the way that you can interpret it. And then what does he go on to do? Does the same thing for cosine. Okay, using the result from section 157, does a very similar thing for the cosine function. Section 159, which I'm not going to go through, he looks at e to the power of x minus 2 cosine g plus e to the power of minus x. Compares this with section 153, where he takes, so this effectively becomes 1 plus x over I to the power of I minus twice cos g plus 1 minus x over I to the power of I. Now, remember in section 153, the form of the integral function that we were looking at was a to the power of 2n minus a to the power of n z to the power of n cosine g. Twice, 2 times that, plus z to the power of 2n. So in this case, we take a is equal to 1 plus x over I, z equals 1 minus x over I, and 2n is equal to I. So we've got to sort out this because this doesn't seem to quite match. Okay, 2 cosine g. However, if we remember that e to the power of x over 2, e to the power of minus x over 2, or minus a half x, is equal to 1, then we can stick that in here, 2 times this, and then we get e to the power of x over 2 is 1 plus x over I to the power of I over 2. Z to the power of n is 1 minus x over I to the power of I over 2. And everything matches up perfectly. Okay, so then he goes through roughly what the method that he presented in section 153. He goes through that to find a factorization for this. Now, this seems like a really strange thing to try to factorize, but there is a point to it. He derives some quite interesting results in the subsequent sections from the factorization of this. So I'm not going to go through it because it'd take too long. However, I do just want to jump forward to section 162 to just point something out that may be a little bit confusing for anybody that's reading this. So where are we? 161, 162. Okay. So this expression such as this here. Okay, so we've got 1 minus, in fact, let's where does this come from? It comes from here. So we've got 1 plus 4 b minus c, let me see, x plus 4xx over pi plus b minus c squared. Okay. So I'm not going to go through how that's derived. It's not, once you've got your head around the stuff that I've done earlier in the video, then this is fairly straightforward, to be honest with you. Although it's messy, but it's nonetheless, it's elementary, it's straightforward. So what he does is he sets b equal to 0. And what he ends up with is this expression, 1 minus 4cx plus 4xx over pi plus cc. So those of you with sharp eyes will realize that there's something not quite right here. Okay, with how we interpret this from a modern perspective and how Euler is interpreting it, they differ. Okay, the interpretations differ. Because from a modern perspective, if we were to set b equal to 0 in here, what we would expect to get is either one of the following expressions. So 1 plus minus 4c plus 4xx over pi plus cc, or 1 minus 4cx minus 4xx over pi plus cc. Either of these would be acceptable if we were to replace b with 0 in this initial initial expression. But Euler ends up with this expression, Now, it's not that he's made any error in his calculation, as far as I can see. It took me a while to really realize it's just how he's interpreting what is written here. He interprets this expression that I've circled in red. He interprets it in evidently this way. Okay, so this minus sign here effectively just belongs with the 4cx. So whereas we would typically see the minus sign as multiplying the whole of this expression, and in particular the numerator, multiplying the whole of the numerator by -1, and hence yeah. So okay, I mean, there's different ways to write it. We would think about it as multiplying the whole of the numerator by -1. Euler doesn't see it that way. He sees it that 1 minus, with a minus here, 4cx plus 4xx over pi plus cc is what we would now understand as 1 plus minus 4cx plus 4xx over pi plus cc. Okay, so it's just the 4cx. So this can be a little bit confusing, right? At least that's the interpretation that I provide for this, that seems to make Euler's reasoning make sense. And I'm pretty sure that Euler was competent enough to know what he was doing, that he didn't make simple algebraic mistakes, especially on a repeated basis, okay? Because he uses this notation repeatedly. So if it was an error, I wouldn't expect him to make it more than once, to be honest with you. It's Leonhard Euler that we're talking about. This is not some some novice. This is somebody that's highly competent at algebraic manipulation. So the only sensible explanation that I can provide for this is that Euler means something different by this notation to what we typically understand from a modern perspective. So it's worth bearing that in mind if you do go through sections 162 onwards. This notation is consistently used in this way. Okay. And I think that's it. I think that's everything that I want to go through in this video. So it just gets a bit messy, to be honest with you, for the last few sections. If you've got the patience to work through the algebra, as far as I can see, it all checks out perfectly. So it's fairly elementary in that respect. Now, that says nothing for how Euler actually managed to figure this stuff out. That's an entirely different thing. That is what always impresses me. The actual calculations that he does are fairly elementary in many ways. But actually thinking in the first instance to use a technique in a particular way, it's an entirely different ballgame. And how he's managed to do these things, that'd be something that I'd be much more interested in trying to find out, which I don't know how I would ever figure something like that out, how he's actually arrived at the idea to use a particular technique in this or that way. But his creativity is it's off the charts. It really is impressive. Okay, so I'm going to finish this video there because we're already up to an hour and a quarter. If there are any questions that you have, because I've covered a lot of ground in this video, as with some of my previous videos, it's been unscripted, so I've probably not explained everything terribly clearly. If you do have any questions, please feel free to ask. I would like to go through some more of Euler's work. I'm not sure what I will go on to next, but chapter 13 is a really interesting chapter. Maybe I'll go through some of that. But if you have any ideas about anything that would be good to go through, that you'd like to see on my channel, please feel free to let me know. Don't forget to subscribe, hit the like button, leave a nice comment. If you would like to make a contribution, you can visit my Buy Me a Coffee page, and you can do that there. But I will leave this video here. Thank you for watching, and I will look forward to seeing you in the next video.